If we're measuring the rate of a reaction, we need to consider how fast or how slowly that reaction goes. We can do experiments, and let's say we could take a look at, in this particular thing, after 10 seconds, 20 seconds, 30 seconds, I see what the concentration of hydrochloric acid is, and I say 0,2, 0,1, 0,05. And they say to me, what is the rate of the reaction between 10 seconds and 20 seconds. Remember what rate is? It's divided by time. So I take the change in concentration, 0,1 minus 0,2, and I divide it by 20 minus 10, and I will then get a rate of change in concentration over change in time. I could do the same thing between 20 and 30 seconds and then compare the rate of the reaction at those two different junctions. We often get asked how to make the reaction go faster, but you can also be asked how to make the reaction go slower. And obviously it's just the opposite of all the things that would be how you would make it go faster. The way we have to explain the rate of the reaction is using something called collision theory. And collision theory says that the more often we can get the particles to collide, the faster the reaction will take place. So, in terms of pure theory, when I increase the temperature, collision theory says the kinetic energy of the particles increase, and therefore they will bump into each other more often, and therefore you will get a faster rate. If I've got gases in the reaction, I can increase the pressure that pushes the particles together, and in pushing the particles together, I land up with them colliding more often. If I've got a solid, I can increase the state of division, and I can do that. The particles are then more exposed to one another, and I increase the number of collisions and therefore the rate of the reaction. If I've got a solution or a gas, I can increase the concentration. There are then more particles per unit area, and they can collide more frequently, and therefore you will get more particles colliding, and therefore a faster rate of reaction. If you add a catalyst, how can I explain that in terms of collision theory? A catalyst improves the orientation of the molecules. Therefore, they are able to collide more effectively, not more often, but more effectively, and therefore the rate of the reaction increases. If I were to take a look at this reaction over here, copper oxide and sulfuric acid. Copper oxide is a solid, sulfuric acid is a solution. And we really don't care that much when we're doing rate what the products are. Well, if we needed to measure, we'd need to know if they were a gas or a solid, and whether we needed to do the mass or the number of bubbles or something like that. But let's take a look specifically now at copper oxide and sulfuric acid. I'd like to increase the rate of the reaction. I can increase the temperature. I don't have to say of what. Increase the temperature. Increasing the pressure will make no difference because I do not have gases here. I can increase the state of division of the copper oxide. If you just say state of division, you're not getting your marks. You've got to say of the copper oxide. I can increase the concentration of the sulfuric acid. And then you can't just say I'll add a catalyst, because the catalyst needs to be able, you need to describe what catalyst that is. We now need to take a look at energy profiles. And in energy profiles, there's actually a lot of definitions that you're going to need to know, because you firstly need to know how to draw the graphs, but then you also need to know things like the activation energy. And the activation energy is going to be from the reactants up to the activated complex. Let's get those two definitions. Activation energy is the minimum energy required to start a reaction. The activated complex is a temporary transition state between reactants and products. You've then got, this is the shape of an exothermic graph. What is an exothermic reaction? Where the potential energy has been transferred into thermal energy, releasing heat. And what is an endothermic reaction? Where thermal energy has been converted into or transferred into potential energy. In other words, I have got more potential energy at the end of the reaction than at the start. So we've got the activation energy, we've got the activated complex. You'll need to be able to label these type of graphs. These are the reactants. the end is the products, and you've then got between reactants and products the delta H value. What is delta H? It is the heat of the reaction, and that is defined as the net change of chemical potential energy in a reaction. Remember that your delta H value is going to be negative for an exothermic reaction, and that's for exo. And for an endothermic reaction, your delta H value is going to turn out to be a positive number. So that's your energy profiles. That's taking a look at energy changes in the reaction. What would happen if I put a catalyst into any of these reactions? The catalyst will, well, you get two types of catalysts, slow down catalysts and speed up catalysts. And slow down catalysts are called inhibitors, but we don't normally look at them too much. They would increase the activation energy, but what a normal catalyst is going to do is it's going to decrease the activation energy. How does it do that? A catalyst speeds up the rate of the reaction by lowering the activated complex, and does that by making it easier for the molecules to meet. So it lowers the activation energy and in that way speeds up the reaction. In itself, a catalyst is not changed at all. If we look at a Maxwell-Boltzmann distribution, this is another way of taking a look at the energy of particles. We've got the number of particles, and then we've got the kinetic energy of the particles over here. Now, over here, we've got lots of particles with this amount of energy, and not so many particles with a high energy. Notice this is a low energy, and this is a high energy, whilst for temperature 2, I've got more particles. I can actually go and I can draw a little line there. That whole area, all of those particles have enough activation, at least kinetic energy, that is above the activation energy. So on a Boltzmann curve, they're always going to tell us the activation energy, and whichever one has got more particles after the activation energy is the one that is at a higher temperature, and this would be a lower temperature because there are less particles with lots of energy, and you're able to interpret a Maxwell-Boltzmann curve like that.